So I'm the chairman. So welcome to the fourth ReNewQuantum meeting seminar. And today we are pleased to have Jørgen Andersen, who is going to tell us about Resurgence analysis of the Witten-Reshetikine-derived topological quantum field theory. Thank you, Jørgen.
The reference point to call these.
Yeah, so thank you very much. Hello? Yeah. So thank you very much, Marcus. Yeah, let's get into it right away. So of course, what we're going to be interested in is the Reshetikine-derived TQFT. And so these are TQFTs indexed by an integer k. And they're really defined, well, I mean, a subset of it, the TQFT, it's called the TQFT tau k. And so a subset of it is that if you have a closed three-manifold M, and you have a knot inside it, and then this knot is colored by representation lambda, then the Witten-Reshetikine-derived invariant will be a complex number. And of course, the Reshetikine-derived work really was sort of a rigorous construction of what Witten had proposed a few years earlier. Namely, he considered SU2 quantum Chern-Simons theory from a path integral point of view. And so then these same invariants, so this is some kind of normalization of this invariant here, is simply this path integral. And the beautiful thing about this is that these path integrals, they are still not well defined, as we know, right? But somehow Reshetikine-derived were able to construct these invariants completely rigorously and combinatorially. And nowadays we can address these invariants, you know, either via modular tensor categories or via conformal field theory or via quantization of moduli space of flat connections on surfaces with labeled punctures. Okay, so let me just go very quickly through a couple of, actually three conjectures in this field, which are sort of the main big conjectures in this field, and then show you how resurgence actually is some kind of Rosetta Stone for all of this. So the first one here is the asymptotic expansion conjecture. And it's the one that you would simply obtain if you just naively think about doing asymptotic expansion to this integral here, imagining that it is a finite dimensional integral. So it's an oscillatory integral. You expect it to concentrate up primarily at leading order at the flat connections, which are the stationary points of the Chern-Simons functional. But if you look at a full asymptotic expansion, what you would expect is a sum over Chern-Simons values for SU2 connections, meaning for the flat SU2 connections. Then e to the 2 pi k times those faces times k to the some power, and then times a series in 1 over k, which you would typically expect will be divergent. And there's only finitely many different SU2 Chern-Simons values, so there will be a finite sum of such divergent series. And to best of my knowledge, this conjecture is still open. Quite a lot about it is known, but it's open in the general setting. Now, there's another very important conjecture in this field, which is due to Renat Kashayev, and that's the one that sort of pertains to the knot theory of the story. And so if you take the example of the three-sphere, you take a knot inside it, and you take a label which is technically not allowed in this TQFT. So it is the first label just outside the range. It's namely the label that has quantum, the first one that has quantum dimension 0. But you can still make sense of the knot invariants for those. And then you normalize by the corresponding invariant for the unknot. You take the log, you divide by 1 over k, you take the limit as k goes to infinity, and Kanchayev's volume conjecture here in the MM formulation is simply that this is the volume divided by 2 pi of the complement. And then I would say that there is a third one, which is much newer and really is about integrality and categorification. So that one has to do with the Gukov, Pei, Putrov, Waffa new invariants. So far they have a definition via string theory as BPS indices. But let us contemplate them for a second here. So they're really indexed by spin C structures, A here. And what they should give is some kind of power series with integer coefficients in Q, where Q is supposed to be e to the 2 pi I over K, linking to the K in the WRT invariance.
Jan, can you remind spin C structures? They're from what kind of set? Finite set?
They're finite set. A finite set for homology spheres. They're finite set, and I think
right. The first homology which
it's affine on the first homology with set 2 coefficients.
Okay. Yeah.
In general, so the conjecture is that not only does these power series exist, but actually there exists some kind of Kovanov type homology, which is indexed by A, bigraded, and such that if you take the Q Euler characteristic of this series, of these groups, you actually get this series here. Okay, so I'm going to talk a lot more about all of these aspects of the theory. I just want to outline that those three conjectures may seem rather different. They're certainly very different in nature, all three. One is the asymptotic expansion conjecture. The other one has to do with the volume conjecture, which isn't quite, strictly speaking, part of the TQFT. And then there is this integrality and the categorification. But I claim that they're really united somehow through resurgence. And so let me try to go a little bit into this. So let's go back and we start with the asymptotic expansion of the quantum invariance. As I said before, the generic phenomenon will be that one gets divergent series. So, you know, in math and physics, how do we deal with divergent series? Well, they very often come up in both math and physics. And so I am now going to go very quickly over the next about 15 slides, because I think this community knows a lot about them. So if you think this is too quickly, please have a look at your mail, because I think you all received the mail with the slides. So I'm just going to go really quickly over this. But the whole point is simply that you have a divergent series. You would like to produce a holomorphic object such that the asymptotic expansion of this holomorphic object, again here, is the series. And not for all series, but for some series, you can do this via something called Borel-Laplace resummation. Just show you here briefly, the Borel transform. This is the formal transform on series, which just does the following thing here. And notice that it takes series with powers of z to the -1 to zeta positive powers here. I will actually later in the talk work with the opposite convention, but for now it's like this. Well, this is a formal inverse of the Laplace transform, as it's stated here. I don't want to go into also these aspects right now, but it has to do, of course, with Picard-Lefschetz theory. There's Maxime covered this very nicely in his first talk in the series. So I really want to just skip to this one here. The main point is that this sort of theory resurgence is really been pioneered for this quantum Chern-Simons theory by, well, in part by Witten, but also by Stavros Garofilidius, and then by Gukov, Mourinho, and Putrov. And the main basic idea is simply to think of the SU2 connections modulo gauge as a kind of curve inside the complex connections modulo gauge. And so simply think of this as a curve integral, and now try to see if one can imitate some kind of middle dimensional Picard-Lefschetz thimble theory for these integrals. So that's the physics motivation. So let me go on with the math. So I want to come back to this asymptotic expansion again. And what I propose now is a sort of collective resurgence conjecture for Chern-Simons theory. It's not just my conjecture. I mean, it's the whole community's conjecture, because it really assembles a lot of conjectures from the field. But it has sort of a 1 to 5. And so the first one says, well, these series here that you see in the asymptotic expansion, they should always be Borel summable. And now the generalization of the volume conjecture, because you see, if I just go back a second here again, we cannot expect that the quantum invariants will grow exponentially fast. They simply don't. They only grow like k to the some power. So there's no naive analog of the volume conjecture. But the true nice analog of the volume conjecture is simply that there is resurgence, meaning that these series are Borel summable and their poles will exactly be all the complex classical Chern-Simons invariants. And since the volume is the extremum of the imaginary part of the Chern-Simons over complex connections, flat connections, this will determine the volume. Next thing is that these meromorphic functions, the Borel resummation of these series, are supposed to somehow satisfy some kind of wall crossing structure, and in part be determined by these wall crossing structures. And then the C hats of GPPV, well, they're really obtained by some kind of Laplace transform of a certain contour applied to these Borel resummed series. And then the radial limit conjecture also of GPPV then states that the original path integral we were after, namely tau k, can exactly be recovered by an asymptotic limit of this type here. And so if you somehow now start a little differently, by starting by a 2, then there's a kind of chance that you could actually maybe even define the theory without having to first prove this theorem and derive all the asymptotic series and then finally prove 1 to 5. You could namely try to somehow start with the classical Chern-Simons values, determine the wall crossing problem, and thereby determine these meromorphic functions, then determine the C hats, and then determine the quantum invariant.
Oh, sorry, Jan. Does the hat mean that this series with integer coefficients are again resurgent and belong to the same stuff?
Yes,
yes.
Okay, they are basically some kind of resummation of these. I will show you what I mean in a little second. But the main point somehow is that there is this chance to actually obtain this path integral in a reverse way, and by somehow starting at 2 instead of starting at 1, or actually starting at 0, which is this asymptotic expansion. But there's also, of course, in this case here, since we know so much about these invariants, a possibility to just verify all 1 to 5. Okay, but as we've discussed here before, somehow we have the ambition of trying to sort of start at 2 and then just simply obtain exact results from this process that is shown here on this slide here. Okay, but this is very general. Let's get to some concrete stuff. So, well, before I do that, I should just recall a little bit about this radial limit conjecture and about the C hats. So the conjecture says that if you have a closed oriented rational homology sphere and you take the set of spin C structures and you take a spin C structure A, then the conjecture says that there are invariants of Y, which is some rational number, some positive integer, and then this C hat A, which modulo these two fudge factors here is an integer power series in Q. So the further very interesting thing about this is that this guy here is supposed to be convergent in the unit disk. And for infinitely many values of k, if one performs the radial limit outward in the disk of the C hat here, then after this kind of recombination, which answers Maxim's question, so there's supposed to be some kind of recombination of the C hat B's, which is some very elementary gadget here, just involving the first homology and the linking pairing, such that you obtain the quantum invariance from the C hats.
What is KAA?
What is KAA?
Yeah, it's something which depends on, well.
Sorry, I don't see K. Oh, it says LK. This is the linking pairing of A and
it's
B.
a linking, okay.
Because
it's a linking for the pair of
A
spin
and B.
structures.
Yes, exactly. There's a little natural pairing. I mean, it's basically the same as the pairing on H1 with the CMOD2 coefficient.
Okay.
So two times the class bounds, and you can do some intersection.
Yeah, if it's integral homology sphere, there's really no.
If it's integral homology sphere, there's no T. This is gone, and you just take the limit.
Okay, just one function. Okay.
Yeah, there's just one C hat. Okay, so this is the conjecture of Gukov, Pei, Putrov, and Waffa. And so I just illustrated here that, we have the quantum invariants, which are indexed by integers k. But now we see a richer picture, namely, we are looking at something that is defined inside the disk, which is the C hat, the GPPV invariant, which we don't have mathematical definition for yet, but there's very strong evidence from string theory that this exists. And the nice thing is that this gadget here, when you take all these radial limits, you are supposed to recover the quantum invariance.
Maybe just one comment. Maybe it should be said that this was worked out in full detail by Lawrence and Zagier and by Hikami long ago.
Well, for certain manifolds, right?
Well, for certain manifolds, yes.
Yeah.
But,
I will get to
that. The fact that this structure is there has been known for 20 years, right?
Right. Okay. So I mean, the fact that
let's give credit when proper, right?
Oh, sure. That's right. But so that is true, and that is math credit, but it is constrained to examples.
Yes. Also, this proposal is constrained to examples, as far as I understand.
You are right.
Okay. So if we are just accumulating examples, let's maybe first mention the people who got out the first examples.
Yes. No, you will see them on the following slides. So indeed. So Zagier and
but I'm confused. Lawrence. This Zagier, Lawrence, and maybe Rozansky some time ago. But did they consider this Z A hat invariance of Gukov and others, which is quite recent? I'm confused what was known before about this second line.
I mean, these invariants were actually constructed by Lawrence and Zagier in terms of mock modular forms, completely written down.
Yes.
Yeah, but it was really special classes, Seifert manifold, which is not representative.
First they did the Poincaré sphere, then Hikami generalized this to safer surfaces with three general fibers. And then, there was an extension to slightly more general class of examples.
Yeah, but still remaining inside integral homology spheres. Sorry, yes, certainly that. And second of all, remaining inside cipher-fibered manifolds and not dealing with all cipher-fibered manifolds, just dealing with certain special examples. And I don't think that there was the bold suggestion that this would work for all integral homology spheres. This was, I mean, I saw the development also and heard people talk about it, and it was perceived as something that worked for those examples. It was seemed to be extremely special to the situation, working with specific mock modular forms and just seeing everything fitting. Okay. Let me leave that discussion among you guys. So I just note that there is this fantastic, nice general suggestion, but our evidence so far goes to cipher-fibered manifolds and no further. Okay, so let me just. However, so what now became the case actually was that GPPV gave a proposal, a very explicit and proposal independent of quantum invariance as to how to define C hat. And so let me just recall this very briefly. So I'm going to take an oriented weighted tree. So gamma is an oriented weighted tree, and the weights is M here, where V is the set of vertices. Then I look at the adjacency matrices, or matrix, sorry. Down the diagonal, it is simply just given by these weights here. And then off the diagonal, it just tells you whether vertex I is connected to vertex J. And we're going to assume that the determinant of this matrix is non-zero and that m to the minus 1 is negative definite. Then we get an integral homology sphere out of this picture, the plumbed manifold. And what you do is you just take every vertex and replace it by a little unknot with the framing MV, and you link two such guys if there is an edge in the graph.
So is it a Seifert manifold?
Yes.
Oh, sorry. Yeah. It's all. You see, the Seifert manifolds is manifolds with S1 action. Yeah. So it's very, very special.
Absolutely.
It's
Absolutely.
Kind of
we will get to other things later in this talk. Don't worry. But I agree. This is very special. But at least there is a definition of set hat in this case. And as far as I know, this definition here is new. Okay. Now, for this plumbing graph, there is a completely, I don't want to give the whole, long derivation of this. Maybe we can ask Sergey or one of the other authors of this to give us a talk on this. But there is a specific formula for these invariants. And moreover, there's actually by now a proof by Gukov and Manolescu that says that if these two manifolds are the same, that you get from two different trees, and there are several trees, and many trees that give you the same manifold, but it's known by Neumann's theorem, then they can be related by Neumann moves. So what these two guys have done is to prove that this construction here is invariant under Neumann moves. So this is really an invariant of plumbed manifolds. Yes?
Ian, since I kind of forgot what Sergey actually did, and he is not here, is it kind of a combinatorial definition of this Z hat?
Yes. It's just a specific combination of products of theta functions that you multiply some kernel onto and take a residue. And so it's completely combinatorial from the graph.
Okay.
And then there was the question, is this really an invariant or not? So the proposal was these guys here gave a formula, and then these two guys here proved that it really is an invariant.
Yeah, it's some kind of Kirby calculus.
Yeah, exactly. It's kind of Kirby calculus. It's Neumann move.
No, it actually should be much simpler because the Seifert manifolds its surface with some orbifold points. Nothing else here at the end of the day.
Yes, but that's right.
And this is a kind of and these trees are just continued fraction, maybe.
Yeah, absolutely. Yeah. That's what they are. Okay. So there's no sort of surprise in these sort of plumbed presentations and so on. But the point is somehow a specific definition of these gadgets here, this series. And so now I would like to turn to what I've done together with William Mistegard, who's my former PhD student. And so what we've done is that we analyzed all Seifert fibered integer homology spheres. And so they are indexed by integers P1 up to Pn, which are all co-prime. And let me just first give you an overview of what we have done and then go through the details of it. So the first thing we've done is to actually show that pi0 of the moduli space of SL2 C-flat connections is actually the same as pi0 of the SL2R and the SU2 moduli space, glued along the U1 moduli space. And it turns out that those components are exactly indexed by the different Chern-Simons values. The next thing we've done is to take the Utsuki series of these manifolds, and then we have Borel resummed them and applied the Laplace transform to this. And we have shown that that is exactly equal to these invariants here, these set of hats defined this way here. And then finally, what we've done is to take these invariants and look at the limit as k as the parameter q approaches e to the 2 pi over k, and shown that you obtain the quantum invariance back. And since we have explicit formula for these Borel resummation of the Utsuki series, we can see that the poles are exactly the same as the sets of Chern-Simons values.
And do you understand this? In this case, omega is a torsion classes, are rational multiples of 2 pi I, yeah?
All of them.
Oh, yeah, in this, yeah, for this.
Yeah. That's right.
No volumes here. Okay.
No volume. No volume.
Yeah, and just kind of to be on the right page, it's sort of computations with some explicit functions like product of theta functions, no kind of integrals over symbols like no Chern-Simons.
Oh, no, there is. I mean, there is. Let me actually go through this now.
Maybe let me ask a question before you start, Jørgen. Where do you even get in the first place the formula for Z0?
Oh, so there is an explicit formula by Otsuki for C0. But actually, if you let me move on two slides, you will see what C0 is.
But what I wanted to ask is it known that Z0 has to do with the perturbative expansion of Chern-Simons, or Otsuki writes some unrelated series?
No, it was well known from the very beginning how he constructed it, that this was supposed to be the asymptotic expansion at the trivial flat connection.
I mean, supposed to be, or like one just analyzes the path integral and
No. I mean, it was kind of guessed that, you know, it's a long story of many actors that have, you know, Rosansky is some to mention here, Stavros should be mentioned here, many people, Don Sagir and so on. I mean, it was a development over time, and the whole field of sort of finite type invariants. Tang Li also should be mentioned here.
I'm not asking a question about who did what. I'm asking a question: is there a theorem which says, you know, here's a recipe for taking perturbative expansions of path integrals, and you get the Otsuki series?
I would say that we have not yet seen a complete perturbative analysis of the Chern-Simons path integral that would give what you just said.
I see.
So I don't know of a proof that the Otsuki series is the asymptotic expansion coming from the trivial flat connection. Because in particular, you would have to somehow understand that there is an asymptotic expansion to be able to talk about this and so on. So no, there isn't, but it's certainly expected and believed.
Jørgen, when we're talking about this, can I ask, is it related to this Kontsevich-Kuperberg, Fürsten-Lescaut series?
Yes. I mean, there are various attacks on this, you know, configuration space integrals. There is also a way to take the universal, I mean, you know, it's also obtained by taking the universal LMO invariant and composing with a weight system. There is tons known about this series here. Okay. But Otsuki really defined it as a certain kind of number theoretical expansion of the Resurgence invariant because it lives in a certain number field. And then, you know, I mean, it's really a cyclotomic integer, and then you do some expansion to that.
But this Lescaut invariant is somehow really defined, like modeled on the perturbative Chern-Simons theory, right?
Yes, but so, you see, it all has to do at which level you ask this question here, right?
Yes.
So if you, because if you want proofs, okay, so then you should start with the Resurgence invariant because that's the only thing that's well defined. But if you want some manipulation with path integrals, since we don't really know what they are, it could mean many different things, right?
No, I guess I'm just asking, like, is it known that the Otsuki series is the same as this Lescaut invariant, or Kontsevich-Kuperberg Fürsten Lescaut invariant, which is also an invariant of like integral homology spheres, and it's also a series.
So is that one finite type?
Yes, I think so.
Because there's a way to address this via finite type invariants. For example,
yeah,
the first non-trivial finite type invariant is only one, that's the Casson invariant. So therefore, at that level, they would have to be proportional then, and so on. And actually, I don't know what the status is, whether those two have been proved to be the same to all orders, for example.
So is it clear that Otsuki is, so I'm sorry, just one more. So is it
I
clear
really would like to move on because
okay,
then
I'm letting you
yes,
move on.
Please, let's not disturb Johan from the main road. I mean, we can discuss this later on. This is not really essential to the seminar.
Yeah, okay. I really would like you to show you the end of this talk also. So, okay, let's move on. So here's the link that you obtain this invariant. And so the work I'm really talking about, you know, really heavily builds on the work of Lorenzo Rosansky on these quantum invariants. And it's absolutely clear that what we did is totally inspired by the work of Gukov, Marino, and Putrov. But, you know, you pick QIs such that you have a link presentation like this, and then you do surgery and you obtain this cipher fiber 3 manifold. Now, so the first thing we proved was that if you look at all the Chern-Simons values and you look at the Chern-Simons functional, it turns out that that's actually injective on the components. So for 3 fiber, it's actually injective on SL2C moduli space. But this can't continue because they're continuous fibers for more fibers. And we're dealing with the general N case here. And so if you take P1 up to Pn and call that capital P, then it turns out that all the Chern-Simons values are of the form minus m squared divided by 4p. So answering also very clearly what Max asked before, namely, are these rational numbers? Indeed, they are. But then the nice thing actually is that if you look at the inclusion of the SL2R connections, the S22 connections into the SL2C, then that turns out to actually be an isomorphism on the level of pi 0. So we can see the via Chern-Simons invariant classical ones, we can simply see the components of this moduli space. Of course, you don't expect this for general 3 manifolds to be the case at all, right? Okay. Now, and here comes the sort of very explicitness that you have about these invariants, something that I think we have for no other 3 manifolds. Because I'm now going to introduce a very specific rational function, namely this G here. And so this is not mine, this is indeed Rosansky and Lawrence who introduced this function. So that's what they saw. So they introduced this function here, and that has indeed integer power series expansion. And then the whole point is simply that if you take the Borel resummation of Z0, then you get exactly this G function here, modulo the simple variable change here.
So Ion, should we? I mean, at least should I know what is Z0?
Yes, Z0 is the Otsuki invariant.
Yeah, but I don't remember. I understand.
No, and so Z0 is the perturbative series associated to the trivial flat connection.
So this is what Vivek asked. So you understand it as an expansion at the trivial connection, and that's it.
Yes.
As a formal series. No,
yes,
no alternative way to think.
No. So that's right. So well, first of all, I should say, let me go 2 slides back, that 3, namely, Lawrence and Rosansky established the full asymptotic expansion of the quantum invariants for these cipher fiber manifolds. So they analyzed them explicitly, and you can actually really, maybe, I mean, one can add that there were some maybe analytic estimates missing, but I have a former PhD student, Hansen, who provided all the analytic estimates to show that the expressions that Lawrence and Rosansky have really gives you the full asymptotic expansion of these quantum invariants. Therefore, we have access to Z0, which is the contribution from the trivial flat connection. And that stands alone because all the other Chern-Simons values are uniquely associated to other components of the moduli space of flat connections by this. So there is a well-defined Z0 to be talked about, and it is already known, it has been proved that that is the same as the Otsuki series in this case here.
What is P capital here?
That's the Borel resummation, so just a Borel transform.
P,
so the inverse
P
of
capital, P, it's a number.
Oh, P capital. P capital is the product of the PJs.
Oh, okay.
So, yeah. So this gives you a very explicit formula for the Borel transform of Z0. And then, of course, you can just look at this guy here and you can analyze where are the poles of this guy. And you see that it will be exactly the set of Chern-Simons values. Okay. Now we can actually somehow, from this, we can consider a very specific contour integral of this meromorphic function. Namely, you take these 2 curves that run in the complex plane like this, and then you take this Laplace transform of this guy here with a 1/z here. And then the claim is that this rewrites as Q, where Q is x of 2 pi I tau, into Z hat, which is defined by GPPV. So that's the theorem. So this is sort of verifying this Resurgence package, right? Or showing you that this set hat here is really given as expected by a Laplace transform of the Borel resummation of the, in this case, the Otsuki series.
Is it also a character of some vertex algebra?
It might well be. I mean, here it is very explicitly. So people who are vertex algebra experts can probably answer this. Okay, let me move on again. So what we then did was we took QKT. So we take the root of unity e to the 2 pi I over k, and then we perturb away inside the unit disk with t. And instead of just taking the limit as t goes to 0, what we did was that we considered the full asymptotic expansion in t of this q of this c hat in this variable. And so what we're saying here is that for every Chern-Simons value, there are sort of uniquely defined polynomials in k of degree at most n-3 for every power of t. So there is a power series with coefficients in polynomials with rational coefficients such that the full asymptotic expansion of c hat along this ray here out to the boundary of the unit circle starts with the quantum invariant, and then it is expanded like this in these series in T with coefficients being polynomials in K. And so all these polynomials are also invariants of the three manifold, of course, because the C hat is invariant, right? But so in particular, the radial limit conjecture is true because you have this leading order term is simply the quantum invariant. So if you like, it's sort of a strengthening of the radial limit conjecture because it's a full asymptotic expansion towards this limit. And then, in fact, moreover, what we can do is we can actually show that if you do the usual Laplace transform, so along the real line of this B of Z0, and you evaluate that in 1 over tau, and you add to it all of these residues here. So these are the residues over all the Chern-Simons values of this guy here, then that is exactly C hat on the nose. And so in fact, it turns out that you can then take a limit as tau goes to 1 over k. And in the limit, what you will find is that the quantum invariant is expressed to you as a Laplace transform applied to this evaluated k, and then this sum here of residues. Where this is a, you know, this guy here is a conditionally convergent series. Okay, so it's not clear this is convergent, but it's actually a corollary of previous theorems that this series is convergent. Okay. So that's all for Seifert fibered manifolds. Okay, so let me, yeah, okay. Let me move on with surgeries on the figure 8 knot. So here you see the figure 8 knot, and you can do P over S surgery on the figure 8 knot, and almost all of them are hyperbolic. I think there are 9 exceptional surgeries on the figure 8 knot that gives you a non-hyperbolic manifold. All the rest are hyperbolic. And so a very important ingredient in understanding the quantum invariants for those is Faddeev's quantum dialog. So the Faddeev quantum dialog is the following function. So it is S gamma of Z. It is X of this explicit integral here, where you do a contour integral along the real axis, but you go a little bit above 0 in the complex plane. And so this expression here is good when the real part of Z is less than gamma plus pi. Okay, so the point about it is that if you now introduce the following explicit function here, so chi of n comma k of 2 variables x and y, so it has some sign, and then it has some explicit phase factor here. And then it has this particular quotient of 2 Faddeev quantum dialogues. And then it has cotant and tangent to x and y. And then it is simply just an application of the residue theorem to show that if you take this function here and you integrate it along a cross product of two contours, and those two contours is just inside the complex plane, in between the lines real part equals to 0 and real part equals to 1, and then it should enclose, you know, m over k where m runs through this set for C1, and m plus a half over k where m runs through these for C2. Then if you apply the residue theorem and you use the functional equation that the Faddeev quantum dialog satisfies, you will recover the Resitikin-Tureev invariant expression for this when you use the Color-Jones polynomial formula by Tang Li for the figure 8 knot. So this is a formula that Hansen and I proved many years ago. And we actually started analyzing the asymptotics of this expression here as k goes to infinity. And we did some work on this, but we were not able to actually fully push this through because it's kind of a little bit complicated what's going on here. So let me detail a little bit about it. The main thing that we couldn't do is the following theorem. And so, you know, what is a good approximation for cotangent in the complex plane? Well, it's actually plus or minus I, depending on whether you're on the upper or the lower half plane. So of course, along the real axis, terrible approximation. But when you just go a little bit off the real axis, it's extremely good approximation. It's actually an exponentially fast approximation to the function. So if that's what it says here at the bottom, that if you look at imaginary x and imaginary y, which is bigger than 1 over k, then this here is exponentially close in imaginary x and imaginary y to just this sign that you see here, because the product 2 i's is a sign. So the main thing is that you would like to take the cotangent and tangent and simply replace by these signs. And so what you have to prove is that this integral here is 1 over O of 1 over k if you want to do asymptotics. And it turned out to be extremely tricky. So I spent 2.5 months working on this during this COVID lockdown, and finally we somehow got it with William. It's tricky. I would love to discuss this with people at some point if they're interested. I do not ever know how to give a talk on this because it is 50 pages of estimates. And what really is needed is very strong estimates on Faddeev's quantum dialog and then the classical dialog in order to see that this decay actually happens. And you have to somehow worry about all the different branches of the dialog, and you're moving up and down the branches, and you are switching the sectors where you approximate the quantum dialog. And so for this contour, it has to be divided into very small pieces that depend on the surgery coefficients, R and S, in order to get this estimate going. So it was surprisingly technical. It just required 2.5 months of not doing anything else at home. But so that was nice. But okay, so once you have that, well, then what you can do is you can simply use the standard approximation of Faddeev's quantum dialog by the classical dialog. So you write the logarithm of the Faddeev's quantum dialog as the dialog plus a remainder term, and here's the formula for the remainder term. And then I will get to that in the end of the talk if I get there. Some estimates on this guy here, because they're very strong estimates on this guy here. And so the thing is that you can simply just then focus on this phase function here that comes out by just taking this leading order asymptotics of the quantum dialog, which is given like this. So it has these two dialogues, plus it has this quadratic term in the variables x and y. And so Hansen and I already did sort of the semi-classical part of the story. We namely looked at the map, the specific map that takes x comma y to representations of the fundamental group of this surgery on the figure 8 knot, and we showed that that map is a surjection from the critical points of this function here to the flat SL2C connections. And in fact, there's this little, I didn't want to spell this out, but there is a slightly stronger expression that says that we get a bijection between certain equivalence class of critical points and then these flat connections. And moreover, this function here is exactly the Chern-Simons function on these flat connections.
Jørgen, I think I missed something a little bit ago. That function you wrote down in the first place with 2 quantum dialogues in it.
Yes.
You write that function. Is it because you've taken triangulation of the figure-8 knot complement into 2 tetrahedra? What is the source of this function?
Yeah. You could imagine nowadays that was what I would have done, but that would be if I looked at the, my invariant with Renat coming from quantum Teichmuller theory. But this is not what I've done. This is something Hansen and I, this expression here goes back to Hansen and I a long time ago, actually some 25 years ago or something like this. And all we did was, you see, if you look at the Resurgence explicit formula for this invariant, it involves quantum factorials. And the Fadeev quantum dialog satisfies the functional equation, and that allows you to express any quantum factorial as quotients of 2 Fadeev quantum dialogues. And therefore, it turns out you could get an expression. So it's also combined with that Tang Li, long time ago, actually established a very beautiful formula for the Collar-Jones polynomial of the figure-8 knot in closed form, also just involving quantum factorials.
Somehow, ahistorically, if I, looking back from today, could I arrive at this expression in this kind of manner?
By doing what?
By taking some triangulation of the figure-8 non-complement. I think there's maybe 2 tetrahedra there. You might imagine 2 tetrahedra means
yes.
of these factors.
You cannot derive, you cannot, with the current existing technology, go that way. So Renat and I have a TQFT which uses triangulations, right? And indeed, the invariant for the complement of the figure-8 knot is a quotient of 2 Fadeev dialogues, but then integrated over a non-compact cycle, named the real line. You see, this is not the case for this guy. This is an integral over a compact contour, and it simply comes from the residue theorem. And so today we do not know precisely how the AK TQFT, so the TQFT with Renat, how that's related to the Resurgence array of TQFT. We expect somehow that resurgence is the answer, okay? That when you do resurgence analysis of this, you will discover contributions from all the branches, all the complex Chern-Simons contributions, and or all the branches, all the critical point contributions, and one of them most likely will be this AK invariant, namely the one corresponding to the conjugate of the hyperbolic representation. But these are conjectures, we don't know, and it's even very weak conjectures at this point. So no, yeah. Okay, let me push on. So here's the main theorem. So we have been able to show in this explicit example by using resurgence of Laplace type integrals. So it's a generalizing work of Malgrange and of Pham, that there exist resurgent power series that gives a full asymptotic expansion. Furthermore, these guys are Borel summable, giving resurgent functions, and the poles are exactly the Chern-Simons values. That's expected. And furthermore, oops, sorry, it seems I'm missing. Okay, I'm missing one slide, but this basically this says it. So first of all, so we have proved the asymptotic expansion for the quantum invariance of surgery on the figure-8 knot. In this case, you have formulated for integral homology spheres, 1 over p. And that, what really results is Borel summable asymptotic expansions. And the reason is simply because, you rewrite the quantum invariant into, here, you take this here and you put in the full asymptotic expansion of the quantum dialog that I'm going to get to in a second. And then you have an oscillatory integral which the Lagrange and Pham resurgence work applies to, and it has to be jazzed up a little bit in order to work. It doesn't just fit exactly. So we generalized it a little bit, but not by much, and then it actually gives this result here. So this is really hyperbolic manifolds for which this really works. And we see that, you know, the Chern-Simons values are not just you know, they are non-trivial, Maxime. They're not just rational multiples of pi squared. Well, sorry, I mean, for the SL2C they're not, but for SU2 we don't know if they all are. Probably they all are, right? Okay, so, but you see, all of this really leads to us wanting to understand much more about the asymptotic expansion of the Faddeev quantum dialog, because we really, I mean, so what you should expect is the following: that a formula of this type here is derivable for any three manifold. Some, you know, finite dimensional integral over a compact cycle gives you the quantum invariant. I think it's not very hard to derive this, and it is expressed in terms of quotients of Faddeev quantum dialogues. And then you will be faced with doing a similar analysis to this in order to replace the quantum dialogues by dialogues like this. And then you have to be able to somehow identify the critical points of the phase function with the flat connections like this. And so that's kind of a scheme to try to somehow start with the Resurgence invariant and derive, you know, something like this for all three manifolds. So this is still open, and I don't know if this can be done, but I expect that it can. But I want to now move on to research and analysis of meromorphic transformations. So this is a preprint I put on the archive yesterday. So, and I'm rushing a little bit because I'm kind of pressed for time now if we want to get through this. But so the setting is extremely natural. So the setting is, consider, you know, an open subset W in the complex plane. Consider a meromorphic kernel, which is defined on that open subset across the complex plane. And so look at restrictions of this kernel, where you just fix one variable, the one in W here. So then you get a meromorphic function on C, and you can consider its pole divisor. And now you pick a contour, which is in the complement of the pole divisor. And I'll get back, I mean, this contour can be very general. It could have boundary, it could stretch off to infinity, all kinds of things. Something that is sort of typical like a Lefschetz thimble kind of contour. Imagine that. But you can also compact components and so on. And now I want another set U, an open subset of C, and this subset should be connected, and 0 should be in the closure, but not in U. And then I consider another meromorphic function F, and I look at the following rescaling of F, simply just elementary rescaling of the variable. And I now further require on F that for the gammas that are in U, the contour is in the complement of the pole divisor of the two functions. That means I can try to consider the following curve integral. So just multiply the kernel onto this meromorphic function and integrate it over this contour. And if this thing is well defined, so I define the subset of meromorphic functions for which this is well defined to be notated like this, then I have some meromorphic transformation which takes these kind of meromorphic functions here to holomorphic functions. And what I'm interested in is to try to understand the asymptotics of this transform as gamma goes to 0. And so let me just tell you, for example, there are a number of very classical stuff involved here. So for example, the Fourier transform, the Laplace transform, the Mellin transform are all examples of this type here, right? And moreover, let me really quickly go through that. You know, here's this fits Faddeev's quantum dialog, right? Because the kernel is this guy here, the function is this guy here, which you're scaling by gamma. And so you see that x of this guy here, where the integral is given like this, we just saw before, that's indeed the Faddeev quantum dialog. But it doesn't stop there, right? I mean, there are tons of examples. The gamma function is given like this. The 1 over the gamma function is given like this. Riemann's zeta function is given like this. And Gauss hypergeometric function is given like this. I mean, there are so many classical functions that are given by such curve integrals of elementary functions. Okay, so I think not hard to convince you that this is very, very general and an interesting setting. And what I'm after is an asymptotic expansion of, let me just quickly go back and show to you again. So I'm after an asymptotic expansion in gamma of this expression here. Okay, let's go down here. And so the point is, what I can do is I can take, so F may have a pole in 0. So I can take its Lorentz expansion in 0. That will be convergent in some specific radius of convergence, this Lorentz series, namely the distance from 0 to the next pole. And let's say the pole order is n0. Then I simply just take the Lorentz expansion of F. And now I assume that all of these modes here of the kernel exist. So take the kernel, multiply it by set to the m, and integrate over the same contour. And then I can do sort of an asymptotic expansion guy, or want to be at least for the beginning. It's simply a transformation that now starts in the same spaces where all of these are defined, and now it goes to formal series in gamma with coefficient holomorphic functions in W. And I just propose this expansion here. So I claim in the next theorem here, well, actually, so what I want to show is that under certain conditions, this here is the asymptotic expansion of this. So I have to understand lots of estimates, right? Okay. And so let me show you the condition under which I can show this. So here comes some technical assumptions, but they are needed. So I assume that the contour gamma omega can be deformed to a contour where I now remove 0. So I'm allowed to move the contour into 0. I further assume the following technical thing, which is maybe easier shown on a picture. So I just switch to the picture. The assumption, so here's an example of an allowed contour. So you see it's very general. But I assume the following. If you take the line from 0 to a point on the contour, and you take the tangent line at that point, then the angle between the two, cos of that should be bounded below by some constant for the whole contour. So you remember that, of course, that when is cos 0? Well, cos is 0 if you go out to a point on the contour. I don't have that here on this contour, but suppose I have some circle. If I go from 0 out to a piece of a contour that's on the circle, then of course cos of the angle is 0 because the tangent is orthogonal to the line to 0. So that I will disallow. It's a technical assumption, but it's important. All contours that I can think of can be deformed to such contours. So therefore, you assume that there's some lower bound to cos of the angle. And then you have to assume the following decay properties. So you have to assume that the kernel can be bounded by some exponential factor times a constant depending on omega times k to the some negative power. So typically k will have a pole in 0 of order k0, and that's why you allow some property like this. And this, so this is away from 0 on this contour, but all the way up to. And you assume that F can be bounded by, whatever is sort of, it's blowing up at the pole at 0, but then you assume that it can be bounded by this gadget here times some constant. Okay, depending on gamma. And so if you make these two assumptions, what you can prove is the following theorem, namely that this gadget here, the operator itself, has a full asymptotic expansion in the Poincare sense in terms of this power series that I just introduced here, this guy here, and the global estimates are very interesting. So the global estimates is that, if you truncate the series at n, you will get the absolute value of gamma to the n+1, delta, which is this parameter in the estimate, to a negative power, and then a factorial. And there is a very explicit formula for what the constant in the estimation is here. So I'm really strongly running out of time. So the rest will be even faster than so far. But let me just try to go through it in 2 minutes then, because I don't want to go massively over time. So this is the asymptotic expansion. Now, if you take this asymptotic expansion, you isolate all the negative terms in the expansion and the positive terms, and you now introduce a formal Borel transform, which is actually the opposite of what I had before. So positive powers go to positive powers. That's because I have a 1 over and the Laplace transform. In a second, you will see this. I define this formal transform like this. Then here is the inverse of the Laplace. Here's the Laplace transform, where you're integrating out, and now where you integrate depends on theta, some angle, and you take phi to be, you remove all the negative powers plus a few more powers, which depends on the pole size of the kernel. Then it turns out that you can prove the following. The positive powers is a Borel summable series, and here's an explicit formula in terms of curves integral for that Borel resume some guy. And so the fact that one has an explicit formula, in this case here for the Borel resummation, means that you can really analyze resurgence properties. So I go on to that. So if you make a further assumption, it's very natural and satisfied in many, many cases, namely that you take this function phi, which is f minus the negative powers in 0, you assume that there are lots of principal parts, of course, of this function, and you assume that the sum of all the principal parts can be made into a convergent series, that's what this slide says, such that the function itself is equal to the sum of all the principal parts plus an entire function. Then you can actually provide an explicit sum formula for the Borel resummation under some analytic conditions. And that allows you to get hold of all the Stokes coefficients by the residue theorem, very simply. So it simply gives us a huge supply of divergent series, Borel resummable, where we understand the resurgence properties and we understand the Stokes coefficients really well. Let me show you an example for the Faddeev quantum dialog. So I have the kernel here, I have the function here, the integral is given like this meromorphic transformation. So it's well known, right, that if I take this 1 over sinh and look at its Lorentz expansion at 0, it's given by Bernoulli numbers. So therefore, the asymptotic expansion I looked at before is like this. And that, of course, is just given by derivatives of the classical dialog. So you just see this here as the asymptotic expansion to order n of this logarithm of the Faddeev quantum dialog. And now what you do is you simply just pick a theta between minus pi and pi. You rotate the contour by this degree theta. And that's important because this integral expression for the Faddeev quantum dialog, it does not work everywhere for all gamma. This one here requires that the real part of gamma is positive. But if you turn the contour by degree theta, you can actually have a new set of gammas, namely where the argument is between theta minus pi half and theta plus pi half. And so therefore, actually, for all gamma which are not on the negative real axis, you can get integral expressions for the Faddeev quantum in some band, and this band is described here. And so therefore, what you can do is actually for all these different bands, you can prove a full asymptotic expansion of the Faddeev quantum dialog. And I want to remark that this is closely related to the estimates that Stavros Garfilides and Rinat Kashayev has in their recent preprint on this subject, but theirs is restricted to real part of gamma being bigger than 0. And this is somehow imposed because they're using some advanced techniques from the theory Resurgence to do it. But so that's our theta equals 0 case. So we really have a more general theory that applies for all theta and therefore applies for all gamma, which is, as I said before, on the complement of the negative real axis. And Moreover, there is this very nice series expression for 1 over sin z, which sums over all the poles, and you reorganize the terms into a convergent series. This is uniformly convergent on the complement of disk neighborhoods of the poles, so very beautifully. And I want to rush through this, but the thing is you can very easily compute the Laplace transform inverse of the series to be equal to this. And when you then insert that into, so I'm using the formula from the previous general theory I gave you before, you end up with the following very nice explicit expression for the Borel resummation of this series, where you can very easily see what all the poles are and all the residues. And this formula matches exactly with Garofalidis and Kitaev's formula for theta equals to 0. So that they are the real part of gamma bigger than 0. So you see, you can answer all kinds of questions about Stokes coefficients, resurgence, and so on from this expression. So sorry about rushing so much for the end, and thank you very much for your attention.
Thank you very much, John. Very good. So, other questions from the audience?
Yeah, your formula relating the Chern-Simons invariant to omega, you always had this modulo z, but the formula certainly suggests that there should be some more precise version of Chern-Simons, which is actually a number, or not just defined modulo z. Do you have some idea what that might be?
Could you help me with what you mean by modulo z? I mean, where
Chern-Simons is equal to omega or multiplied by 2 pi or so. So relating your residues to a Chern-Simons invariant.
Yeah. Mm-hmm. So back to Seifert fibered manifolds and this expression here.
No.
No.
One back. Chern-Simons on the left-hand side.
This has quantum Chern-Simons on this side.
Okay.
Is that what you want, or do you want the classical Chern-Simons?
You had formulas, equalities for Chern-Simons modulo z, of course.
Jan, I think he means the identification of the poles with Chern-Simons.
Yes, this one, or something like this. Yes. Identification of the poles with the Chern-Simons values. Yes.
So this certainly suggests that there should be some more precise version of Chern-Simons for which you really have an equality and not modulo. Something like similar things to Attila Patoli, so certainly not this kind of local definition. But
so yes, I should actually say here that this was just a short way of writing it on the slides. We actually do get exactly the Chern. I mean, all the integer lifts of the Chern-Simons is equal to the poles.
Okay.
So you know that your Chern-Simons functional is not well defined on a 3-manifold, right? It's a real modulo integers, but there is a sort of cover that you can go to on connections modulo a smaller gauge group, where you take out the homotopy type of, I mean, or you know, and then it's really a well-defined invariant into reals, and there it's equal to the poles.
Okay, thank you. That was exactly the question.
Yeah. Okay. So it's very nice that it covers all these higher towers of poles, and this is certainly something that's been seen before by Marcus and by Sergei Gukov and others also. But we see this for all these Seifert fibered manifolds. We see this.
So, Jörg, I have two questions, sort of. Maybe it's a reference. You were speaking about rank 1 case only, like SL2, SU2.
Yeah.
How much of this is expected to be true, say, for SLN and SUN?
So since you said expected to be true, yes, I would expect that all of what I said today is true for all ranks.
Yeah, but I mean, not just like hope for a happy future, but your
Yes.
technique seems to be very much bounded to the rank 1 case.
No, I mean, no, I don't think so, actually. No. I mean, if we talk about what the techniques should be able to do, I don't see anything that obstructs going to SUN. So you have to take the quantum invariants. There are also explicit formulae for the quantum invariants when you work out everything from the modular tensor category. They are given again in terms of quantum factorials. Now it is much more complicated, but it's still the same. This can be rewritten via Fadeev's quantum dialog, and the asymptotic expansion of the quantum dialog is completely understood now, right? I mean, this is under complete control, and so therefore there will be stuff about complete. I mean, what I would say is that the thing that I would say is the biggest challenge is this. If you start with quantum transimmence theory for the compact group, it is this thing where you want to understand, remove these things that come out of the residue theorem. So these factors here are in some sense not natural, I think. They are just there in order to give the right residues. So I believe that such a residue expression here could be derived for SUN. But what I do not know is how one will see through the analysis to establish something like this. In fact, for general 3 manifolds, I think this is a big challenge, even for SU2, to do this. This you will have to see some kind of very nice organizing mechanism, because this was really, really difficult to do.
Yeah, and the second question is for this SL2 case, you have, and the knot, you have this A polynomial and you have this Q difference equation. So you can kind of approach in a different formal way, looking for the solutions of that A hat, whatever, and how much of this, I mean, it's sort of reference question, maybe, how much of this resurgence can be derived from the analysis of the Q difference equation. I remember Marcus
maybe
said
quite a bit.
about...
Maybe quite a bit. Sorry, I wanted to. I don't have the slide, but I deleted a few slides, so this was the short version. But in the longer version, I actually had some stated the result that we have together with William on the Collard-Jones polynomial, and so that is resurgence with parameters. And there, what happens is that indeed the A hat gives you recursion relations, but somehow I know that Marcus has done some very nice work in this direction, starting with the recursion relations, and it relates to our invariant with Renat. And I also know that Sergey has done some work on that together with Manolescu, where they somehow really use this recursion relation.
But so it's an alternative to what you said. It's an alternative.
Yeah, exactly. So I mean, I could maybe derive them backwards, but somehow I get the resurgence out of the properties of the quantum dialog. But it's also, if you look at Stavros' work with Renat, they also use, I mean, they're using this resurgence, and they get the resurgence results by looking at the functional equation that the quantum dialog satisfies, and that equation is the analog of the A hat. I mean, that is the A hat for the quantum dialog. That's the functional equation that this guy satisfies.
Okay, all right, thank you.
But I don't use that. I mean, actually, so if I just one remark about this last stuff here, if you have a look at this paper, it uses only very simple elementary analysis. All the proofs in this paper here are sort of just using, elementary one complex variable calculus, and then a little bit of estimates and calculus. But it's actually possible to get a very general statement, you know, like this one here.
Yeah, so you need somehow some kind of formulas, and then you say that this analysis will give you resurgence in the end.
Yes.
Some estimates for quantum.
So these estimates give you resurgence. So I mean, this part here is only the asymptotic expansion, but this part here is the resurgence. It's sort of the key is to see that the Borel transform is given like this. And then the next step is that you can actually somehow take all the poles, all the principal parts, and typically they will all be summable, and often they will give you exactly the function. But I just assume that it gives you the function modulo a entire function, because I don't worry about it, and then the entire function just goes in down here as a correction term to the Borel resum guy. But this here is a completely explicit formula for this resurgent guy. From this you can deduce all the poles and all the residues and the Stokes coefficients and so on.
Okay, thank you.
Questions?
Yeah, so I was wondering if, Jørgen, do you think this this resurgence analysis of kernels, can that maybe be generalized to Bergman kernels, and maybe that could then be an approach to the SUN case through quantization of moduli spaces?
I certainly think so. I mean, the kernels here. So first, yes. I mean, first sort of statement in this direction is, I would think there's nothing in these techniques that I've used that indicate that there should be differences between one variable and many variables. I don't say infinitely many variables, but I say many variables. And so once you're at many variables, well, then you are in the realm, as you know, as we've worked on together, kernels that come out of, say, quantization, geometric quantization, like Bergman kernels and so on. And this is all somehow local, right? In patches that you do this. And so I would think that this generalizes to such situation. But I mean, now I'm guessing, but I mean, I don't see any reason why one shouldn't be able to somehow do something very general with kernel, with operators given by sort of kernels like the Bachmann transformation.
Right, because then you wouldn't have to guess the right residue formula, and then maybe things would be more natural, more naturally.
Precisely, and I really expect that then you will see contributions coming in from the surrounding Higgs bundles from the SUN moduli spaces very naturally out of this picture here.
Right.
More questions?
Jørgen, just a short question, sorry. First, thank you for a nice talk. Hi, yes. We know that, well, there is a relation to cluster algebras somewhere hidden here, and to quantum cluster algebra. So do you expect that this insight can be helpful in your approach?
So the way I would think about that is via sort of similar comments that Jan made about a hat.
Yeah, Jan actually stole one of my questions, so that's
yeah, okay. So
sorry about that.
Yeah. Well, maybe I'm missing something, but I don't need them here in some sense. I mean, here I derive the resurgence properties by this formula. And maybe what one can do, I mean, of course, this formula in general could be quite complicated, right? Because if the pole structure of the original function is very complicated, then this gadget here could be quite complicated. But I would say that the virtue of this is that I do not need a recursion formula in order to derive resurgence, something one normally does. Here one has resurgence sort of from these analytic estimates instead. But this is very new, so I don't know. I mean, maybe this can be explored and one could figure out somehow what is the role of a hat? What is the role of cluster variety structures in the moduli space in relation to this? I don't know at this point.
Yeah, okay. I can make some comment, but maybe it's sort of a negative. If we look
That's
not
okay.
for Q-difference equations, but the differential equations, yeah. So instead of a hat, you have kind of differential equation. And then indeed you have cluster structure, which comes from these Warros symbols, which seems to be okay. But when you want to prove, for example, that the WKB expansion is given by a Resurgence series, then it doesn't help much. At least I know that this old paper by Simpson, which goes back to 90s, he just did more or less the same direct analysis as you are trying to do with explicit analytic estimates. So I don't know whether it will be easier for Q-difference equations.
Yeah.
Oh, sorry.
I mean, well, the techniques that I have been using is sort of, in some sense, the same techniques as people are using with the Mellin transform when they analyze, differential equations using the Mellin transform. Not exactly the same, but the ideas may be somewhat the same. So you readdress the resurgence into an analysis problem in that case instead also, and estimates. But yeah. Okay, sorry. Yeah, Maxime.
No, just it's got a bit lost at the end. You have this analytic result about one-dimensional contour integrals depending on parameters, yeah, something like this.
Yeah, right.
But it's not directly applicable to your previous figure 8 node because it's two-dimensional contour, or is it? Yeah.
But I mean, two things to say about that. First of all, it is directly applicable because it is applicable via the asymptotic expansion of the Fadeev quantum dialog.
Yeah.
Okay, that's
but here you get two-dimensional
absolutely.
Yeah.
Yes, but as I was sort of alluding to before, I do not think that there is anything in this that is sensitive to dimension 1. I mean, I did it all for dimension 1 first because I wanted
dimension
to recover
kind
this.
of like playground, not directly.
Yeah, but that's the first thing you do. Okay, and I think that much of it is simply just turning on n. I mean. There will be some things that are different, as we know, when you go from one to more variables, but the essential part should be the same thing.
I have a question, which is actually a question for Maxime, if it's okay. It's,
sure.
So Maxime, in your old in your paper from like '94, when you discuss perturbative expansion of Trent-Simons, sometimes you say that you should take a cyclic connection, and sometimes you don't. And so I'm always confused about whether this perturbative expansion arguments you give there, if they make sense at the trivial connection. Can you comment on that?
No, trivial connection. If you have, if it's isolated, yeah, of course you can. Yeah.
But so why do you and also some other people sometimes say you want a cyclic connection?
Just isolated point. Cyclic.
Yeah, I mean, it's because of technicalities in running the asymptotic expansion.
No, otherwise you have additional finite dimensional integral about more connected components for this connections. That's it.
Yeah, and you may not have transversality, so they might be more complicated. But
yeah,
I mean, this is all doable.
But it's very old. Yeah, nowadays I think people know how to do it. Yeah, it's parameters. Yeah.
So I mean, in this Malgrange story that I was referring to before in FAM, you really do not need non-degeneracy. But of course, this is an infinite dimension, so that's more tricky. I don't know. But all of this is in finite dimensions, so you don't come into these problems. But I mean, it's well known that if you don't assume acyclicity, it's a problem. And I really don't think, and I would like to advertise this as some nice open problem, that one should really deal with the full perturbation theory from let's just say from the physics point of view of Chern-Simons path integral. So really try to write out an expression that makes sense for all flat connections and that you somehow propose a well-defined integral over each component, which is supposed to be the asymptotic expansion of quantum Chern-Simons theory done from the path integral point of view. This has not been done, and I don't think it's straightforward easy. I mean, it will be quite involved because it will involve, making sure all the things with Radameister torsion, and all kind of things really work out and gives you a measure on the set. And there are singularities for the flat connections moduli space, and there are things which is not transversely cut out and so on. So it's quite complicated.
But this was precisely the question I was asking Maxime. At least at the trivial connection, and trivial connection, assume it's geometrically isolated, but it has cohomology, so it's not somehow isolated in derived sense. I'm just confused whether because like in this Axelrod-Singer and also in Maxime's old paper, always people say things like acyclic connection, and but then sometimes people say, okay, trivial one is okay, and I just am, I want to know what is the state of the art? Is it if you do the Feynman diagram expansion around the trivial connection, is it converged? Is it well defined? What is the situation?
No, it certainly doesn't converge.
No. Of course, each term is a convergent integral, but the sum is asymptotic.
No. Just each term.
Each term, yeah, no, definitely get exactly this.
But I mean, do we know all the technical details? Has all the technical details been worked out?
I think the younger people know better than
Okay, because I mean the equations that cut out the flatness could be horribly singular right there.
Yes, no, but it's also a general idea. I think it's about reduction in BV formalism when you get finite dimensional mass, but it's okay.
Yeah, maybe.
Yeah, no. I think it's like.
But I would love to see. So if somebody in this audience knows a good reference where I can see the full perturbation analysis of the trivial flat connection done, so that it's really rigorous math definition of what all the coefficients should be, I would love to hear from them and hear that reference.
I'm not sure that's exactly what you're asking, but there is this paper by Catanion Mioff, Remarks on Chern-Simons invariance. So they do something in that direction at least. So you can define perturbative expansion around.
And also Koehler-Roschetichen now involved in this, I think.
Yeah, I know, but I mean, has it converged to some explicit expression that I could sit down and check whether that's equal to, say, Olsuki series? Or, I don't know. Anyway, I just feel that there is a lack of, certainly if I extend the question to all flat connections and components and so on, I'm worried this isn't.
Even trivial connection, I've looked a little bit and I have not succeeded in finding such a thing.
So you can generalize Axelrod-Singer's story to the trivial flat connection or to any flat connection that you want using these methods of Catanion and Mioff, but they're older, I guess.
Where is it done?
No, actually, I don't understand the problem. If you have isolated flat connection, you just use the kernel, all integrals will be convergence. Yeah, so it's really no problem. Yeah, no, I've considered this inverse hit kernel for flat connection.
But what about zero modes and all of that?
No. If it's a cyclic, there's really no problem.
Sorry, the partition function will be a function on zero modes. I mean, it's not a number. Yes.
Yes, it'll be a function, and there is this formalism, which is kind of, I think Andrei Losov proposed many years ago. First, you have a solution of this up to homotopy of master equation on a finite dimensional variety at the end of the day.
Okay.
The opinion is it's known how to do this, but
yeah, I think so. Yeah.
I see. But is there any place I can find it actually done?
Yeah. I haven't read it, but what enough and Roschetichen are writing, it's kind of.
I see. Okay, maybe I'll ask them.
I can send you a reference, but I'm not sure that's exactly what you want. But
I mean, I've looked in Catenarium Nev, and they certainly do not do it. I mean, they do not prove a theorem saying that here's what you think the perturbative expansion is, here's what we think the perturbative expansion is, and they're equal.
I don't know. They're not proving a theorem. I think they're just giving a sort of a definition maybe of what one such expansion could be, right?
Do they calculate a single term in their expansion?
No.
Just as a moderator, maybe
Problem.
this discussion is not really related to Johan's seminar.
Yeah.
Be held as a private Zoom conversation rather, right?
Yeah, maybe you're right.
I mean, maybe people are a little bit pressed for time, but I mean, it's not that I don't, because I love that discussion, because I actually agree with Vivek that I can't find this, and I would love to see it done. But maybe we can have somebody talk about this at some point. But anyway, I mean, Marcus, you're in charge of German, and maybe you should.
I mean, you know, I mean, if that's fine with me. Just that, you know, I'm not sure if you know. Yeah. Anyway, I think. Yeah, maybe we should have a different seminar, because I think people are maybe like interested in understanding a little bit more basic aspects of Chern-Simons perturbation theory. So maybe we should have a seminar on this.
That would be great, yeah.
Okay. Okay.
So are there more questions related to Johan's seminar?
I have one more. What was the relation between first part of the seminar and the second part of the seminar?
There were three parts. There were ciphered fibered, yeah, if you like. There was ciphered fibered, there was figure 8 knot, and then there was this meromorphic transformations, right?
Yeah, so the last part.
And the last part is, you know, a generalization of Faddeev's quantum dialog. So Faddeev's quantum dialog is an example there. And so to understand the full asymptotic expansion and get the very strong analytic estimates on the remainder terms was used in the analysis of the quantum invariants in the first part on the figure 8 knot.
I see. So you use the techniques in the last part to prove these estimates in the first part.
Yeah, the asymptotic expansion estimates are used. That's right. But so I realized it was much more general and really something about meromorphic transformations and not something specific to the Faddeev function. It's really, really general. It applies to the Riemann zeta function also, for example, and hypergeometric functions and so on. Okay.
Okay. Thank you.
Thanks.